Do you have a way to turn any 3D point cloud into a solid 3D mesh model? In this tutorial, I will show you the powerful marching cube algorithm to mesh 3D point cloud with Python. This will allow us to go from this kind of point cloud into this kind of 3D mesh and also playing on various parameters. It's super nice to avoid being stuck by other limitation of the Poisson reconstruction, ball pivoting, Delaunay triangulation, and on top we'll build a tiny web app with a GUI. So what do we need to make that work? We have three prerequisites. The first one is a computer with Anaconda or a virtual environment for managing packages with Python 3.10 on it. This is how I test it. The second thing is a 3D point cloud, of course, and the third is some amount of libraries that will be useful to handle all of our processes. That's it. So let's roll now. Okay, so look at that. I have lots of point clouds, square, urban, aerial vegetation, China building, aerial, urban, Tom, Italy. And maybe what I can do first off is to explore a bit what we have under our hand. So I loaded them in CloudCompare just to explore a bit what we're going to deal with. So this is, for example, a super complex point cloud that we want to mesh. So this will be a huge challenge because it's heavy. And yeah, there are a lot of tiny details everywhere that will make it particularly challenging, as you can see. Maybe we can start with something simpler, like, okay, so this is a mannequin. This is from my wife whenever she's designing stuff, which is useful to pose the way a mannequin is behaving. Then we have, what do I have here? I have a tree from a terrestrial laser scanner. So again, this is super challenging to mesh, and this should be adapted maybe as well. And what else do I load it here? This is a chair from one of the other datasets that we saw in a previous approach. Really good. So let's start with a chair. So what I do is I go onto Spyder and I spin off my Spyder IDE. If you don't remember how to do that, I encourage you to look at this other video that explains exactly how to set up your environment. So I have an Anaconda with Python 3.10 and I have Spyder on it as my IDE. So the first thing that I do is importing my libraries. And as you can see here, we are going to use NumPy, Open3D, Sky Image, for having the measure component, and SciPy Spatial to use KD3 to compute a bit quicker everything that we need. So this is our library. So the first thing that I do is right-click set console directory. I will save that, and now I will basically execute the cell. Now we move on to the second component, and as you can see here, this is basically loading all the data set that we have. So Verviers, the tree, the mannequin, the dome, and there's here we can maybe delete. We imported the library. Now we define a list of the name of our data set, and because it's at the same place as our script, we don't need to put in the path. I will just use that directly. So what do I do next? Basically, as you can see here, I'm defining a super simple view function that will load with Open3D and save that in a variable PCD, and then visualize it to make sure that we handle the point cloud that we want to handle. And then I return the PCD so that I don't need to load it 2 times. Basically, I will save that in the variable right after. Good, so I execute that, and then we move on to the third step, which is defining our 3D mesh function. And this is where it gets super interesting. So as you can see, I define a point cloud to mesh function that takes in a point cloud, a voxel size, and an ISO level percentile. So by default, I put that to 50 and the voxel size to 0.05. But of course, depending on your point cloud, you will need to adjust that. And this is where just after, we may investigate something that is a bit more challenging or a bit more smart, let's say. So what is happening in this function if I go within it? The first thing that I do, as you can see, is that I load, like I transfer my PCD points into an MPI array so that I can handle that with the various libraries that we use, so Sky Image and SciPy. Then I compute the bounds of the point cloud and I create a voxel grid. Basically, this is exactly what we do, is we take in the mean and the max and the voxel size, and we create as many points that are the center of this, this little grid on top of the point cloud. Then we create a KD tree. This is for efficient neighboring search. And after that, we compute the scalar field, so the distance to the nearest point, right, which is in here. So why do we do that? This is because we are going to mesh with an approach that is called marching cubes, and this is more or less what you will find in topographic maps, right? If you saw that before, you see that you have contour lines. So maybe let me show you something a bit better. These are contour lines, right? Basically, we are plotting on a 3D lines that goes through all the points with the same height. And what we do with marching cube is exactly this. We are going to compute these iso surfaces, right, by tying in like similar scalar field. And in this case, the scalar field that we use is the height, 10, 20, 30, 40. But in the case of marching cube, this can be anything else that we define. And because we work with point cloud, we will compute the distance from the point to the nearest point inside of our grid to be able to compute exactly how we should create the triangle that goes through this iso surface. And at the end, we will have exactly a mesh that is based on the iso surface for each and every cube that we have, so each and every voxel that we have. All right, so it will become clearer whenever we will use the function actually, so don't worry about that too much at this stage. So if I zoom back again in our code, we have our grid point. What do we do here is basically we stack all of that together and we put that as a 2D array so that we can compute the distance more efficiently, right? So this is using the KD tree. And then after we get our scalar field based on these distances to the nearest points. And this means that we can now determine the iso level based on a percentile of distance. So what do I mean here? So basically, imagine that you have 4 points, right? And this is the green point have the same iso level, and there's one have the same one, but it's minus because it's slower. So these are our grid point. Then we go into step 2, where we create our iso surface. So basically, we plot the line that goes through the same scalar field value. And then based on that, we can create our triangulation. And this is exactly what we are doing. And this is where the iso surface is super useful. And maybe I can illustrate also how the iso surface works for you. So this is my illustration of iso surface. These are our grid point, right, in gray. And these are our original point, okay? So we have the distance to that. And basically, this is used to compute the iso surface by using any of the percentile that we want to have. And as you can see, if we go very low percentile, then we have something that is very tight, trying to match very nicely. So I have a little shift. I just wanted to show you the little shift. Normally it should be on the point. This is what you have. Then if you go at 50%, which is the base value, you have something that is median, and if you go below, you have something that is very loose, so not as tight as the 75 percentile. And this is where it's useful to use this percentile to adjust exactly how you want your mesh then to smooth out your point cloud. And this is very useful depending on how much noise you have, or how accurate it is, how much detail you have. You will need to adjust this kind of parameters. Great, now back to our code. So this is what we do. Our iso level is defined by taking the percentile of the distance and the iso level percentile. This is exactly how I compute it. And then based on that, we apply, as you can see here, the marching cube. And we just take back the vertices and the faces. We could have also other parameters, but at this stage we can leave them, right? This is what we need. Based on that, we will just translate our vertices back to original coordinate system. So the vertices time the voxel size plus the minimum that we had, right? This is a shift, and we create our mesh geometry by adding the vertices and the triangle to our mesh object that we create here. And after that, all that we need to do, it's not necessarily important, but it's computing the vertex normal to have a better visualization of the shading that we could apply on our mesh. So this is a super interesting approach to mesh out any point cloud without computing extra feature like normals, that you will need for ball pivoting, for Poisson reconstruction, and Delaunay reconstruction, and so on. These are things that take out the bulk of the processing, and here if we can alleviate that, this is very good. So this is something that we can now execute and move on to the stage 4, which is loading a point cloud. So which one do we want to load first? The Verviers chair. So this is the dataset 0. Let me execute that. Open here, and as you can see, this is our chair, right? So it's a point cloud which has a density that is not super high, but again, it will be interesting to see what we get from that. So let me close that and go onto CloudCompare and maybe try to take a distance between 2 points, like these 2 ones. So we'll take between this one and this one. Yeah, that's good. So we have a distance of around 4 millimeter. So it will be a bit bulky. Maybe we could take a voxel size of 1 centimeter, and it should make sense, right? So we'll get back to my code. And whenever we enter now point cloud to mesh, you see that we can use our function directly in here, point cloud to mesh, where we pass in the point cloud, the voxel size, and the ISO level percentile. So we'll go very low to be as close as possible to something that doesn't smooth out too much the points, right? And for that, the voxel size in here, we said 1 centimeter should be good. So if I go here and put 1 centimeter, this should be good. And then after we draw the geometry, the mesh, and we show the back face cooling. So I save my script and I launch that. And as you can see, it doesn't take too long. Okay, so very good. This is a very good base to see that we can maybe adjust a bit our parameters. So what could we do? If we want something tighter, let's say we will go down, right, of the ISO level percentile. And as you can see, we go a bit tighter. And for the voxel, we could also move a bit tighter, like taking voxel every 5 millimeter. And this is something that will make the computation explode a bit because you have much more voxels, right? So as you can see, we are a bit tighter, but it creates also a second shape here. This means that we have maybe a problem of alignment. So this is our chair, a bit tighter. And if, let's say, we go to 1 and move down to 5, the ISO percentile, we may have some floating element or some holes, as you can see. But this is where we have something as close as possible to a chair, right? So this will be good. And if I were to go at 50, you will see that it generates a massive like mesh that is maybe really cool to see, really bubble-like, but it's not really accurate. So this is something that we would avoid at this stage. Good. So this is working. Now let's check out what we will have on the tree. Right? So the tree is the dataset 1. Let's visualize the tree. Yeah, this is a tree. Very good, very noisy with a lot of points. So that will be good to have a way to mesh that. So again, I will go at first stage with 10 centimeter voxel size and ISO percentile. Let's go pretty down with a 10% and execute that. And here we go. We have our point cloud that is meshed. And as you can see, it looks really super nice, right? This is something that we can use. It's looked already optimized, but it really looks something that we could use for video games where you have enough detail, and I love it. I love it. But of course, if you want to have something that is not so detailed, maybe we could adjust to have it's like at a 30 percentile, and it will be much more bubble-like. And here we have it, the bubble-like point cloud. So you see that the trunk gets much bigger, but the leaf as well, and it gets cut basically by the extent of the voxel, and this is what you see there. If you want to avoid that, you need to create a mesh grid that is a bit outside what we have. But this is super interesting. And here also what I can say is sometimes it makes sense to inject some kind of semantics. So if you have decomposed between the leaf and the trunk, you can mesh the trunk with one strategy, some kind of parameters, and the leaf with another strategy. This means also that you can adapt the parameters locally. This is also something that could be feasible by using an octree structure instead of a voxel structure. Very good, so it works. Now, the next stage is, of course, to try and automate these parameters, right? So that we don't have necessarily to inject prior knowledge, because this is what we did here. So to avoid injecting prior knowledge, I defined this little parameter estimation that I'm going to walk you through. It's not super like rocket science, but these are some smart tricks that will make your life easier whenever you want to like tune in your algorithm with heuristics. So in here, this first thing that I do is I estimate my voxel size. For that, I use the average distance to, let's say, 30 at least neighbors if you have so many points, and I use my KD tree. So that will take time, okay? So this is something that I show in the course 3D Segmentor, how to optimize by chunking and parallelizing and making sure you have something a bit smarter. So I take the average distance, and then my heuristic is basically multiplying that by 2 to get my voxel size, so to make sure that one voxel holds at least some points and not only one. Then I estimate the ISO level percentile. So for that, I compute the distribution of my distances to get the best percentile, and I exclude the self distance, and then with a coefficient of variation, that is standard deviation divided by the mean, this is what I use to adjust my percentile. So if I want like more spread out, if I have more spread out point, I will have a higher CV, so a lower percentile. And the inverse, if I have a lower CV, this means that I have a higher percentile, right? So this is what I do here, 50 times I1 minus CV, and this is the other way around, and I limit it to the range of 90, right? So after that, I return the two parameters, the voxel size and the ISO percentile level. Now what I can do is showcase how it works for the tree, for example. So let me execute it. And as you can see, we have a voxel size of 8 centimeter and an ISO of 10. It didn't want to go below. So this mostly is aligned with how we found really just before the parameter that we use. So let's use this parameter. So basically I reuse the function before. I just input in it the point cloud, my new parameter that I save, and my new ISO level percentile that I save. And then after I do the visualization in here. So let us execute this. And as you can see, we have our tree that is actually the best of the 3 generation that we did, right? Because you can see here that we have the branch taken out. They are a bit like exaggerated, I agree, but it's beautiful. This is more maybe for visualization purposes, because accuracy wide, this may need to be shrinked down a bit, but overall I love it. I love it really. So as you can see now, we have a fully automated approach to do just what we had. And yeah, the cherry on top is that here are my optimized computation. I'm just going to do that and showcase on the latest one, which is the DOM Italy, right? What would happen. So PCD view, mesh, and visualize. So let us execute that. If I execute that, we have our point cloud in here. Let's move right in it. So what I like here is that it's evenly distributed. So this is the perfect condition to execute Martian cubes. But it's really big and there are a lot of delays. I'm really curious about how this will turn out. It can be really crappy. So let's just close it and wait for the computation to finish. And here we are. We have our results of our Martian cubes algorithm. Wow, I absolutely love it, right? So this is something that we could definitely use for creating collision system, simulations, video games. This is very nice. We also have elements from there. I did not believe that we could pick it up, and also from here. And it's like, it's not perfect. I think you have some default. But if you were to mesh that with a Poisson reconstruction, that will fail Delaunay, it would be very heavy on the computation side. In here, it took maybe around 30 seconds, a bit less. And we have our full mesh for this like big 5 million points point cloud, which is massive. Let me export that, and maybe before moving on to the last stage, import that into Blender. Okay, and I put the geometry to the origin so that we can explore it in Blender. Beautiful, this works. Now the last stage is maybe you want to create an app from that. So this is where Gradio may help you. This is a little like library. Again, you can install it with pip. Gradio as GR. So what did I do here? I have estimate parameter and point cloud to mesh function that are both in here, right? And I just have this little like code. It's around 15 lines, where it will create a little app with Gradio, an interface with the function point cloud to mesh, which is used. As input, I will drag and drop a file, which is our point cloud, and as output, it will generate our 3D model in the window, right? And you can also pass an example. I did not, and this is just to say, if this is the main file that is executed, then launch the iFace. So let me just launch it. And you will see that it will give it to me a little localhost URL, which is this one. And what I can do is basically create a new window, go onto this URL, and you see that I have my little interface with Gradio. And of course, then it's only an extra step to put that on your server or to upload that to Hugging Face. So what we want to do is, as you can see, drag and drop our tree right in here. And once this is done, we can just press on submit, and it will launch our script. And at the end, it will save our file in a temp folder as a PLY or an OBJ object in this case, because the 3D model viewer doesn't handle PLY, so I had to convert it to an OBJ. And then it visualizes it directly in here to make sure this is what you want. And this is done. We have our viewer in here, and as you can see, we can explore our super nice mesh that is derived from our tree with this interface. So this is something that you can definitely give part of the team. There is some work to be done to optimize everything, but again, here if I were to click on download, you see that I have my output mesh directly in here. Voila, we have successfully turned any 3D point cloud that we had into 3D meshes with the marching cube algorithm. So you can extend it, make it more performance oriented, or extend the Gradio application. These are things that we do in the segmental course, but of course, feel free to extend whatever is shared in here. As always, thanks a lot for watching, and see you in the next tutorial. Bye-bye.